So this week we have Sam Bateman, who's going to talk to us about physics of curves.
Wait a moment for the coffee machine.
Yeah.
Right. Today I'm going to tell you about the well, the usual waves of field equations of physics, things like the Klein-Gordon equation and the Boyle equation. They're usually derived using group theory. You start off with the Poincare group, you find its unitary representations, and you find all of these field equations. But that way can sometimes feel a little bit abstract. Today I'm going to tell you about a way which is a lot more intuitive and, in my opinion, a lot simpler, which is to say that I'm going to start with a particle is a point. This particle is going to trace out a curve, something like that. And so I'm going to describe this curve using some map gamma from some interval from 0 to 1 into Minkowski space, R3, 1. And whenever you have a curve, you can build a series of geometric properties or geometric invariants. Let's say I'm at some point here, t. The first one is the velocity vector, which I'll call gamma dot. Then the next one is the acceleration, which let's say points over this way, gamma double dot. And you can keep going. So let's say there's a gamma triple dot, something like that. And then using these vectors, I can start building some one forms. So the first one is the arc length, which I'm going to call lambda. And this looks like gamma dot squared, and then I take its square root. And when I say it's geometric, I mean this is, if I integrate this, this is invariant of the actual map gamma. It only depends on the curve. So it's reparameterization invariant. So it's kind of a 1D version of diffeomorphism invariance. So the next one is the extrinsic curvature. And this I'm going to call kappa. So to build this one, I take gamma double dot. I take the component of it, which is orthogonal to gamma dot. I square it. I normalize it by gamma dot squared. And I take its square root. And this is also geometric. So to see that, I take gamma dot. I take away gamma dot dotted with gamma double dot. If I square this, I will get gamma double dot squared minus gamma dot squared. No. Okay, gamma dot dotted with gamma double dot squared over gamma dot squared. So if I do a change of parameterization, let's say this was t, and I say t is some function of s, then gamma double dot becomes gamma double dot becomes we use dot to denote t derivatives and prime to denote s derivatives. This becomes this plus s double dot gamma dot. And when you take the difference of these two things, the s double parts vanish and you're just left with an s dot. So I'm squaring it, get an s dot to the 4. That's not quite right. Let's double dot plus this, square it. Yeah, I'm squaring it, so until I get an s dot to the 4. and then dividing by an s dot squared. I take the square root, I can and overall I get a ds. So this thing is invariant under reparameterizations. So now to build physics out of these things, I'm going to use these things as my action. So the first one is going to be the arc length. My action is going to look like the integral from 0 to 1 square root of gamma dot squared dt. I'm going to put a constant out the front, which I'm going to call m. And I want to find all of the classical solutions of this action. And the easiest way to do that is to start with the full phase space of Cauchy data. I'm going to say that Q mu is going to be gamma mu at some time, let's say 0. And say P mu is L d gamma dot mu, and t equals 0. And that is going to be gamma dot mu over the square root of gamma dot squared with an m. And so the full phase space, there are 4 Qs and 4 Ps. So it looks something like R8. But not all of these initial data are valid. So if you can see that if I square P, I get m squared times gamma dot squared over gamma dot squared. So this is always equal to m squared. That means I can only use initial momenta which satisfy this constraint. I'm going to bring this to the other side. I'm going to call this phi. So I can only look at initial data which satisfy this constraint. But this constraint also generates a flow in this phase space. So I also have a symplectic form, say omega, which is dp mu, which dq mu. And from this, I get a Poisson bracket. If I now look at the Poisson bracket of q mu with this constraint phi, q mu, let me put a half in front of this. So I differentiate this guy with respect to q, this one with respect to p, and I get p mu. This means that q isn't gauge invariant. Gauge invariant just means it has a 0 bracket with the constraints. So in order to get something gauge invariant, I need to say that q mu must be equivalent to q mu plus some arbitrary constant times p mu. So when I say these are equivalent, let me draw a picture. So this constraint surface p squared equals m squared means that my p lives on this mass shell. Let's have some point here. This is my p. I'm going to say q is equivalent to q plus tp. This is q0. This is q1. I have some initial position here, and that means I can translate in the direction of p. So I get something that looks like this. So this will be a geodesic for a massive particle. And so my reduced phase space is this R8, where I restrict to momenta which live on the mass shell, and Q. And instead of looking at Q, I think of the world line generated by this Q. So this is my point Q here. So where Q is proportional to Q plus T times P. So this thing is called my reduced phase space, or my reduced symplectic space. And this is my classical theory. Every point in this space corresponds to a world line along which a massive particle travels. So another way to see this, another way to think of this quotient thing is my symplectic form when I look at this surface, p squared minus m squared equals 0 is degenerate. And so I need to do some sort of quotienting to make it non-degenerate. That's the same thing as just using this Poisson bracket and saying this Q is equivalent to that. The other point is that this constraint removed 2 degrees of freedom, one by restricting to a surface and the other by this quotient process. So I started off with 8 and I got down to 6. So now to quantize this thing, I need to choose either position or momentum. This is, I mean, the fancy way of saying is choosing a polarization. But really all I'm doing is I'm saying I want wave functions which are functions only of the momentum. So I'm going to say my wave function is some psi of p, which is defined on this mass shell, p squared minus m squared equals 0. So in order to get back, I can consider this as a function of 4 momentum. It can also include a delta, which will localize it to this mass shell. And then integrate over p before you transform it. And this will be my wave function, psi of x. Oh, sorry, this should be minus. So you can see that if I act on this with the box operator, I get down at p squared, which is equal to an m squared, and that's just the Klein-Gordon equation. Okay. So let's move on now to this curvature action. This is a really nice story. You start off with something very simple, which is just a point particle. You said I want to minimize its arc length, and I got out Klein-Gordon theory. So to generalize this, there's a few different ways to generalize it. The most famous one is probably string theory, where you say instead of having an interval, I have something two-dimensional. But in my opinion, a much simpler way to generalize it is allow your action to depend on higher derivatives. Because then we can start using these other invariants, namely the curvature, and seeing what we get out of it. So this curvature action looks like this. I'm going to integrate from 0 to 1. This thing here I can rewrite as gamma double dot squared minus double dot gamma double dot all squared gamma dot to the 4 with the square root. And as I mentioned before, this is invariant under reparameterization, but it also has an extra gauge symmetry. If I take gamma dot and I rescale it by some arbitrary function of time, say f of t times gamma dot, this action is invariant. So this you can think of as a one-dimensional version of Weyl symmetry. I can arbitrarily rescale my metric. So this means because I now have two, and let me drive the equations first. So if you've never seen higher derivative equations before, you can or you can use your Hamiltonian analysis looks almost the same. So my Euler-Lagrange equation is going to look like d squared dt squared dl d gamma double dot minus ddt dl d gamma dot plus dl gamma is 0. So without this term, this would just be the usual Euler-Lagrange equation. But from this, you can kind of guess at what the momentum should be. So from these first two terms, I can factor out the ddt. Now it looks like the derivative of something plus, well, this Lagrangian doesn't depend on gamma, only on gamma dot. So that's 0. And I have the derivative of something equals 0. So this thing, I'm going to call the momentum p mu. Well, I guess I'm not really using indices. Indices. So What? Fourth order equation, I need extra pair of variables, two momenta and two positions. My second momentum, I'm going to call this thing, I'm going to use capital P U. So now my full phase space, before doing any reduction, is now 16-dimensional. So I have small q, I have a capital Q, let's say what that was. My big Q is going to be gamma dot. So I have two position coordinates, small q and big Q. And then I also have two momentum coordinates, e mu and capital. These sit in R16. So the 16-dimensional phase space. But before I do any reduction, let me first show you what the classical solutions look like, just to give you some sense of what these are. So I mentioned there were two gauge degrees of freedom. One was reparameterization of variance. The other was this local rescaling. And so I need to fix both of those gauge degrees of freedom to find the solutions. So I'm going to use this thing called, well, I'm going to fix gamma dot to be constant. This is sometimes called the Einbein.
Can I ask a really dumb question?
Yeah.
How do you know this symmetry of the gamma dots is not just like a residual symmetry of the overall reparameterization? That's the case, you know, like that's just basic bosonic string theory, that's the case, right? How is it like definitely unique?
I guess gamma dot will, or gamma double dot will change differently.
Oh, of course it will, yeah, like, because you'll have the f dot t plus, but I was gonna say that, is that, okay. Okay, yeah, okay.
Yeah,
No, I think that's fine. I think because I just, yeah, if you do like that, so if you say gamma to f, sorry, you do representation and then you hit it with a dot, you'll have an extra term. So fine.
Yeah.
So I'm an idiot, but so that is truly a different symmetry.
Yeah. And it doesn't stop there. Like you can keep going up to, you can have one which depends on the third derivative, which is torsion, and then you get an extra gauge symmetry.
Yeah.
Where you rescale gamma double dot independently of gamma dot, and you can keep going like that.
Thank you.
Fix this extra gauge symmetry. I'm also going to fix gamma double dot be constant. So when I do that, my big P momentum, E mu, now looks like, so this was the L double dot. This is, oh, I forgot one other thing, which is like, I'll stick a parameter in front of here, which I'm going to call it S. So this is now S squared gamma double dot minus gamma dot dotted with gamma double dot minus gamma dot. Because I've used this is always called a canonical gauge. No, this is the proper time gauge. I'll take the time derivative of this, I get gamma dot times gamma double dot, but this is constant. So this term is 0. And then in my numerator, I get gamma dot to the 4 and this curvature. The square root moves on to the denominator, becomes a k. And so in total, this becomes S times gamma double dot over E squared k. Where the E squared and k are just the constants for my gauge fixing. Now the small momentum, E mu, is the L E gamma dot minus P mu dot. So this becomes, you do the same thing, take derivatives of your Lagrangian, get rid of things that are 0. And in the end, you find that it is minus S over E squared k. Maybe it's easier to see if I make this one. Then from the big P dot, I get a gamma triple dot. And then from the other part, I get a K squared gamma dot. And then I know from my overall equation that P dot is 0. So this thing is equal to some constant P mu. And this looks very like the harmonic oscillator equation. If I factor out 1 ddt, it's exactly the harmonic oscillator equation. So a solution of this equation looks like an example solution is, let's say I take P mu to be P0, 0, P0. Then my solution gamma of T looks like E squared P0 over X times K, and of E over K cosine KT, and I have E over K sine KT, and we have E squared over SK times P0 T. There's a T here as well. So if you ignore the middle two pieces, this is just a null geodesic. This is just tracing out a line. This is my light cone. This is just describing a null geodesic somewhere on this cone. But these extra two pieces tell you that you're rotating around it. This is describing a helix, which is wrapping around a null geodesic. So in this picture, it's going to look like some kind of wave like that. So this is where this is Q0. But if I look at the other three dimensions and say where this is Q3, you can see what happened. I have a null geodesic here, and this thing is describing a helix going around the null geodesic. There are a few interesting things to point out about this solution. The first is that it's superluminous. This is moving faster than the speed of light. So to see that, we need to reparameterize such that gamma 0 is t. And when you do that, you find that the free velocity squared is 1 plus x squared k squared over e0 squared e squared, which is greater than 1. Now, this isn't actually an issue because the velocity isn't gauge invariant. So what this means is that this particular curve is gauge invariant. So the gauge invariant object is an equivalence class of helices, all wrapped around the same null geodesic. And the thing they have in common is that they all go around the same way. So there are two solutions for each null geodesic, a right-handed one and a left-handed one. So let's figure out what the gauge invariant bits are. So let me
over there, the gauge was like on shell condition p square equals m square.
yeah.
Here we'll have two gauges and they both correspond to some sort of equations of motion.
Yeah, I'll show you now. Yeah, all this gauge symmetry means we're going to have a ton of constraints. And because there are two gauge degrees of freedom, there are two first-class primary constraints. The first one, phi 1, tells us that big P is orthogonal to big Q. This must be 0. And the second one tells us that big P squared times big Q squared has to be equal to alpha. So you can see immediately they have two vectors which are orthogonal, but they can't be null. So these are two space-like vectors. And then whenever you have constraints, you need to check that they're preserved under the action of the Hamiltonian. And this usually means you have a whole bunch of other constraints. So in total, we're going to have 5. The next constraint tells us that small p divided with big P is 0. The fourth constraint is that small p, well, this one is divided with Q. The small p is also orthogonal to big P. And the final constraint tells us that small p squared is 0. And so you can read off from this one that it's a massless particle, which is why I chose a null geodesic over there. So you're right that you could think of a wave function in 8-dimensional space which satisfies all of these wave equations, but I don't give much hope of solving it. So what I'm going to do instead is try to find the gauge invariant objects in this larger space. So you can see immediately that none of the constraints depend on small q. So actually I need a symplectic form to. So my omega is the E mu wedge d U mu plus a P mu wedge d Q mu. You can see because of none of these constraints depend on small q, that small p is gauge invariant. That means if I take E mu and I consider the Poisson bracket, which some arbitrary linear combination, say epsilon I, phi I, this is 0. So the momentum is gauge invariant. The other things that are gauge invariant are the angular momentum. My angular momentum J U nu looks like the usual angular momentum P mu Q nu minus P nu E mu. This is like the orbital angular momentum. But I also have a kind of internal angular momentum, which comes from the higher derivative parts. E nu Q mu. So this part you can think of as the orbital angular momentum. And this, sorry, that should be a plus. This you can think of as the internal, the spin angular momentum. And then you can check that the Poisson bracket J U nu and some arbitrary linear combination of the constraints is 0. So the gauge invariant objects are the momentum and the angular momentum. And so there are 4 components here. This is antisymmetric. This has 6 components. So in total I have 10, but I haven't yet implemented all of the constraints. So let me do that now. The other nice thing is that these do satisfy the Poincaré algebra. So using this Poisson bracket, it's just the Poincaré algebra. Now to implement the constraints, this one is easy to see. This constraint just means that my momentum has to be null. This looks like P wedge Q. This only depends on the parts of P and Q that aren't that are linearly independent. So this constraint here is automatically satisfied. So it's only these three constraints that I've yet to implement. And I'll claim now that the remaining constraints will force oh, on one last thing, which is the Pauli-Libansky vector. So this looks like 1/2 epsilon mu nu sigma j nu rho p sigma. Well, that's a small p. And I claim that the remaining constraints will force the Pauli-Libansky vector to be proportional to the momentum. And the constant of proportionality will be this parameter s that I put in front of my action. To see this, it's easiest to do if I pick a particular frame. So I'm small p, and I'm gonna pick a frame in which this is equal to p0, 0, 0, p0. And I have this big Q, which we determined was space-like. So I can also choose a frame in which this first component is 0. And then I have rotate in these two variables to force this component to be 0. So I'm left with a Q2 and a Q3. And then I have a big momentum in which I've already used up all of my Lorentz symmetry, so I can't say anything yet about this one. Okay. So the first constraint is that small p out of a big Q is 0. So this forces Q2 to be 0. No, Q3. And this thing is now gone. The next constraint is that small p with big P must be 0. So if I dot this with this tells me that big P3 must be equal to big P0. And the last constraint is that Q squared, P squared must be equal to S squared. I may have called this alpha up here. I really meant S. It's just the parameter or the constant that I put in of the last constraint means I could just rescale Q2 such that it satisfies this constraint. And what I'm left with then, you can just check the components of this one by one, and you'll find that the only non-zero components are the 0 and the 3 component. And it ends up being exactly S times d mu. So that means that the gauge invariant quantities in this theory, which satisfy the constraints, are the momentum and the angular momentum. The angular momentum has to be such that it satisfies this equation. And this is exactly what comes out of group theory. So this describes it's sometimes called a co-adjoint orbit. So in your Poincare group, you have momentum, you have angular momentum, and then you have two Casimirs, your mass and your spin. And this is exactly telling you that you're on the spin S orbit within this Lee algebra.
Like the S there comes from the coefficient in the action.
Yeah.
And this S is the proportionality of Pauli-Lubansky with momenta.
Yeah.
They have to be the same.
Yeah. You find plus and minus S there. I can show you that now if that's not clear. So W0 is the only non-zero one. Thing. And because this has a P in it, this is totally anti-symmetric. This just becomes epsilon mu nu rho sigma big P nu big Q rho P sigma. So you can now read off the components of this vector from over here. And you find that omega 0 is epsilon 0, 1, 2, 3, big P1, Q2. This is P0. From this equation, I read that this must be S. Because this is just the square root of this. This is just, well, plus or minus S times P0. You can similarly show that P1 is 0, or W1, W2 is 0. Last one is W3, which is epsilon 31, 20, big P1, Q2, 0, which again is plus or minus S times P0. So it is true that that S parameter is the same one that appeared in the constraint. It's the same one in the front of the action. Okay. So if I want to quantize this thing, I first have to show that this is the same thing as twistor space. So that's what I'm going to do now. So the momentum E mu, because it squares to 0, that means I can write E mu as pi a pi bar on this one. I can write it as a product of two spinors like this. And the angular momentum and this I just pulled out of Penrose and Ramsar. This is I times omega. Maybe I shouldn't use omega because that's my symplectic form. We call this eta. We bar B minus I eta bar the epsilon E dot minus eta bar A dot I B dot symmetrized epsilon A B. So because this is a two form, we write it as a self-dual and anti-self-dual part like this. So I have this constraint that the Pauli-Urbansky vector has to be proportional to P. So this Pauli-Urbansky vector, you can look at this as the dual of J. This is just J dual contracted with P. Which means that this W mu is the dual is become this becomes 1. So I get eta bar B symmetrized plan A dot B dot is eta bar B dot and B, and this is contracted with I bar B B dot. Contract a spinner with itself, you get 0. So the only ones left over are we get a half just from the symmetrization. Then I get eta B bar B plus eta bar B dot I B dot left over with a I B I bar A dot. But this thing, that's just P. This is telling me that this must be equal to that constant S. This constraint. So now we've gone from momentum and angular momentum to this I and eta with this constraint that this must be equal to S. But this constraint also generates a flow within this the space of two spinners. And so to figure out what that is, either my symplectic form when I translate everything to spinners becomes minus I d eta A d pi A plus I d eta bar A dot which d pi dot. So this means I now have a Poisson bracket. And I call this constraint, let's say phi 6, which is that eta B I bar B minus eta bar B dot I B dot minus 2S. This must be 0. And look at the Poisson bracket of say eta. Its constraint. I get well, let me put in some theta. And this is minus I theta. This tells me that theta A must be equivalent. So this is just some phase. This generates a change in phase. So eta must be equivalent to e to the I theta with itself. And the same thing happens for pi. So pi A must be equivalent to e to the I theta from itself. And so now I'm at least back to the right dimension. So I had free momentum and free angular momentum. I then went to two spinners, which is C4. I have one constraint, which brings down the dimension by 1. And then I have another gauge up, brings it down back to 6.
Well, usually when you take the action of like fields with its constraint, it gives you the gauge transformation. How come you've identified that with U1 and not, let's say, like translational? There's something like that. I don't think that's completely obvious.
Oh wait, I forgot the eta A.
Okay.
That make more sense.
No, okay. That's
Yeah, it's just a phase transformation.
Like the symplectic 2 form before we had like small q, capital Q,
Yeah.
capital Q, capital. Yeah, like 4 different. It was R16, the phase space.
Yeah.
And now the phase space is just eta and pi complex,
Yeah.
which is C4.
Yeah. And well, I had an intermediate step of going to the angular momentum. And I didn't write down what the symplectic form was in terms of the angular momentum because I'm not sure what it is. So this is following the paper I'm following didn't actually go to angular momentum. They went from this some complex coordinate Z, which was effectively looked like big P plus I Q, something like that. And then you find the constraints, maybe that P squared is 0. And from there they went to spinors, and they said Z was, you know, A slide B, something like that. And when you go through their way, you arrive at this symplectic form.
So you have to reduce this phase space somehow.
Yeah. So the proper way is to impose the constraints and then quotient out by the gauge orbits. Whereas I did things a little bit backwards. I found the gauge invariant objects and then imposed the constraints. But either way, you get down from 16 down to 6. You can see, I think I wrote it out. I had 5 constraints. Each removes 2 degrees of freedom. So I go from 16 down to 6.
Sorry, we're 5.3, 5.4, and 5.5 all tertiary.
They're all, yeah. So they're all first, well,
Well, they're not first. I mean, they can't be first class, right? Because they're derived from.
I always get confused when there's between primary and first class.
Oh, so primary is the constraints you get from dynamics, and then first class is the ones that commute with themselves. They like form the algebra. They're like the gauge symmetries essentially.
Right, yeah, they're all first class. The first 2 are primary, and then the rest are secondary and tertiary. The secondary and tertiary usually put on the same level as the primary, as far as I know.
Yeah, exactly. So I'm saying so they're all generating.
They're all first class.
Good.
Okay. So now that I've shown that the reduced phase space is twistor space, its constraints, and quotient out by this orbit, we can now quantize it. The first thing is I need to check that it is quantizable. There's this condition where this symplectic form is exact, so you can write it as d of theta. Well, maybe I shouldn't call it theta. This is theta prime. This is d of theta, and I'll choose theta to be minus I eta A d bar A plus I eta bar A d by A dots. And then because I quotiented out by this orbit, there's this quantization condition that tells you that if you integrate theta along one of these orbits, then gamma now is some circle which looks like e to the I phi times eta A by A. If you integrate this, it should be an integer. So on the constraint surface, this will look like 1 over 2 pi, the integral from 0 to 2 pi 2s d phi, which is just 2s. This tells you that 2s has to be an integer. So now that I know it's an integer, I can now just do canonical quantization. So I'm going to say that eta A is just d pi bar, and then eta bar goes to d pi dots. One of these will have a minus. I think This one has minus. So now this constraint will become an equation. This constraint now looks like pi bar a e pi bar a minus pi a dot e pi a dot minus 2s. Thing on my wave function must be 0. So if I only look at wave functions which depend on pi and not pi bar, this is telling me that it must be a homogeneous polynomial. So I need that psi. You've got my signs wrong. I'm doing like that and that. This tells me that psi must look like some function. Well, I'm just going to have psi must look like some function times some polynomial. You must have 2s of these pi's. This will then satisfy this constraint. And there are 2s of these. This is why I knew that 2s was an integer.
Some, I guess you get 2s plus 2 homogeneity because eta bar is d pi. If you plug eta bar there, it will first act on pi, which will give you a factor of 1.
Yeah.
So I guess you'll get 2s plus 2.
I'm not sure. I know in that book we were looking at, it said 2s plus 2.
Mm.
And I was looking at the one by Woodhouse. He said 2s. So
Like,
I wasn't quite able to.
if you simply replace eta bar in that expression with d pi,
Yeah.
like that expression for s,
Yeah.
then d pi will first act on
Oh,
pi.
right. Yeah, there is an ordering ambiguity.
Yes.
Because the result will be something along the lines of Penrose transform, and the right answer is with a +2.
Yeah. Yeah, no, that is right. Okay, so these that ordering. And I'll get a plus 2 here. I guess it'll be a minus 2, look. Like that. Okay. And now to get back to space time, I can Fourier transform this, which is the Penrose transform. Actually, maybe able to tell me if this is the same thing as what we're reading. So this means that I a dot b dot as a function of x, I'll integrate on p squared is 0. Minus I. My b dot all the way through pi c dot. Actually, no, I think this is different from the Penrose transform. Because my measure is just the measure on the cone. So it looks like BP1.
Yeah, you need to restrict it to a twistor line, but then I think it's the same. Once you localize that to a twistor line, there'll be some way of doing that, like by the instance ratio. This
That's
P,
where
then I'll read the Penrose transform.
That's where the 2 comes from then.
Yeah, I imagine that's what the 2. Yeah.
Okay. Well, the short answer is that this gives you all of the massless spinor equations. If I choose s equals a half, this means I only have one of these pi's. We got that psi a dot is 0. This is just if I use the Pauli matrices. It's just the Weyl equation.
Essentially, right. Yeah. So I'm kind of a little bit curious. So you integrating this over p squared equals 0.
Yeah. Well, what the version I was looking from doesn't have this too. This integral is on the light cone.
Yeah.
So instead of having the pi d pi measure, it just has the dp3 measure. But that might I think that might be where the difference of two comes from.
Because yeah, just thinking of like the twistor correspondence, obviously you're sort of integrating that over the null plane in Minkowski, so this should be localized in twist space, which is a bit weird, right?
P square equals 0 is the light cone, which is CP1 some like. But there's also a Fourier transform which takes you from X to P.
Yeah, I think that Fourier transform is the bit that's going to localize it. I'd imagine that's going to localize it to a twistor line. I can't quite see. It's just yeah, it probably isn't that many lines of calculation to show.
I can probably tell I'm not the most fluent in spinner stuff.
No, this is fine.
But anyway, the short answer is you can get Boyle equation. If I said S was 2, if I said S was 2, I would get if S is 1, I'd get the Maxwell equations. If S was 2, I'd get the linearized Einstein equations and so on. All of these came from that world line action. So you can think of a massless particle with spin as traveling along some helix, going along a null curve. The helix itself isn't a physical thing, but it's an equivalence class of helices. So it somehow has some right-handed twisting motion going around a null geodesic.
That's what they call the flag, right?
It's very similar to that Penrose flag thing. But as far as I know, Penrose doesn't use this helix notion.
No, I've never seen this before. So it's really nice.
Okay.
So S is allowed to be half integer though, right? So you have fermions and gauge bosons.
Yeah, they're all the same.
Spin 3/2 fields.
Yeah.
And any higher ones.
I don't know, yeah. Yeah, I think that's everything I have to say. Are there any questions?
How does it relate to Dirac singleton?
That I'm not sure yet. I think, well, I only went up to curvature. Next one up is torsion. And there you now have first, second, and third derivative. So you end up with a 24-dimensional phase space in 4D, but you end up with 12 constraints. So they each remove 2 degrees of freedom. So you have a 0-dimensional reduced phase space. So I think it might have something to do with that, but I haven't made it very precise yet.
So you can see that we are getting fermions and bosons from here.
Yeah.
Actually, can we see anyons from these kind of analysis?
In 2D. What will happen in 2D? Because in 2D
Crystals won't work.
you'll have an 8-dimensional phase space. But then you somehow need to remove 10 from 8. So I don't think it will work in 2D. Yeah, I don't think it will work. This is quite special to 4D.
So like when we start with just second derivative world line action, we have mass. That's for massive particles. But
Yeah.
when we go to higher derivative world line actions, we end up with spin but not mass.
Yeah.
Like usually I think of higher derivatives as something you add to your second derivative, but
Yeah.
here it's very like the difference is very essential.
Yeah. I've seen 1 or 2 papers where they look at some linear combination of arc length and curvature. So there you'd hope to get something with spin and mass. But then you end up with things go wrong because the curvature action has this extra gauge symmetry, which the arc length action doesn't have. So you end up having, I can't remember exactly goes wrong. I think you've more constraints than you have gauge degrees of freedom. So I think the conclusion was it just doesn't work. So as far as I know, there's no way to get massive particles just from a curve invariant. You can only get massive with no spin or massless with spin.
Are there any more questions? Yes, so let's thank Sam again. And we'll be going to Marty and Ramin on St. Lake Nicholson Suite after this, so everyone is welcome to join.
When do we meet?
6:45.